Okay, so let's look at a stack then. So stack is a data structure, uses the same concept as a pile of books being on top of each other. The simple premise that the book at the bottom you can't get to until you take off the other books on top of it. So in other words, to get to the Hobbit at the bottom, we'd have to take off Harry Potter, Pride and Prejudice, 1984, etc. first, so we could get to it. Otherwise, if we tried to yank it from the bottom, the whole pile would fall over. Obviously, on a computer, we don't use gravity. The data is just the way it's being controlled, but we're trying to mimic the logic of this. And this is really useful because it helps us to do various things. We can reverse a list of data, we can return addresses when we're storing them, but we can also use it in an interrupt. So the states of the registers within the fetch decode execute cycle can be interrupted. The data that's in there gets put into a stack. In other words, a location of RAM that's pre-designated for this. Once you've finished dealing with the interrupt, you need to then put the data back into the fetch decode execute cycle so it can then run again, and therefore you just reverse it. It means you're sort of saving on difficulty of trying to manage where each piece of data has been stored and all those sort of things, because you know that the order it went out is the opposite of the order it'll come back again. When we're talking about stack, it's a last in, first out data structure, or first in, last out, same logic. It has a top pointer. The top pointer starts off at -1, and therefore we know there's no data there. It's null, it's empty. Notice it goes 0, 1, 2, 3. That's very similar to the arrays that we've had before. So if we want to carry out some various actions with this, we must always be checking, is the stack empty or full? And we must also, therefore, push to add to the data and pop to remove data. So if we're going to push some elements into our stack to start off with, we first of all are checking where's the top pointer. Is there space remaining in our stack? We therefore add London, and the top pointer increments to 0. We then do it again with Manchester. It's now incremented to 1. We can keep going. Let's add Leeds, incremented to 2. We then add Brighton in. Again, it's incremented to 3. What's special now, though, is we're at the top of the stack. So when we've created the stack in memory, we'll have given a certain number of locations of memory for that. So in this case, 4. What we then do is we look at 4, max size, in other words, we take away 1, and that gives us the index of that top position. So in other words, position 3. And therefore, we want to check, is it full? If we were to try and add another place to this, so Coventry, there isn't space in the stack, and that would cause a stack overflow. So in other words, a simple algorithm for this is we're checking, is it full first? In other words, we look at the max size, and then if there is available space, we'll then increment the top pointer and add in the new data accordingly. If we're removing, therefore, so we're popping items from the stack, we're just doing the opposite now. So we remove Brighton, and then we decrement or reduce the top pointer by 1. Again, do the same for Leeds. Can keep going. If we want, it's now showing at Manchester, isn't it? In other words, we're just doing the same thing as we're going through. So we're checking, is it empty? And therefore we can remove data. Again, if it's empty, that can cause us problems, just because we would then get sort of an underflow error because there's no data to remove. Effectively, we get an error message. Let's look at another one then. So queues. A queue, different type of data structure, we call it first come, first serve. And again, just like with a stack in real life, a queue is the same as in real life. So the same logic. The first person at the queue is the one who gets dealt with first, and any other additional people get added at the end of the queue. Again, there's some of the same sort of problems with this as well as real life, that I'm sure you've all been stood in a shop sometime and somebody ahead of you is taking ages to decide their order, and you get a bit frustrated. Well, this is the same issue with a queue within a data structure, that we can have delays because of tasks ahead of it are getting served first and maybe taking a long time. However, what it does offer us is the ability that every single task within that queue will eventually get their turn, hence why we use this process in shops. We look at the data structure again, we use an array to create one of these. So can you see that the data structure from the memory point of view is the same thing as we've used before, except it's the way as a programmer we're dealing with it. So in other words, we're now treating that array as if the first piece of data is the front of the queue, and then the last piece of data is the end of the queue. We have a head pointer for this and a tail pointer that are both pointing at those things. Again, there's something with the language has changed here, so that when you add, you now on queue or NQ, and when you remove, you DQ. So let's have a look at it. So you can see here we've got again our 4 stages. We either are enqueuing or dequeuing, and we're checking again, is it empty or is it full? So we can see here we're going to enqueue. We've enqueued Ryan, Greg and Max. The head pointer is still showing at Ryan because that's the front of the queue, and the tail pointer is showing to the next available space. What we're going to do now is remove 2 items, so Ryan and Greg. The head pointer moves across, so it's now pointing at Max, so that's the first position in the queue. Notice, though, that the Ryan and Greg data is technically still there in the queue. It's not necessarily been actually removed. And also what we've got here is we've got available space. Okay, so I'm hoping you can see that there's a problem there, that we're actually losing capability within the structure. So if we keep going, for example, I'm just going to exaggerate this further. We then add in Jenny, so the tail's moved across, the head's still pointing at Max. Max hasn't disappeared anywhere, so he's still the front of the queue. We then remove both Max and Jenny and then add Anna. So now the head is pointing at Anna and the tail is pointing at Anna. We've got a full queue. We can't now add anything else to it, but we've got a frustrating situation where we've actually got 4 available spaces. Can you see that? It's a problem. It's wastage, isn't it? It's not very efficient. There is, of course, a solution to this. We can do what's called a circular queue. In other words, we start to use up the spaces at the front. However, what I would say, I'm just going to go back to this slide, is that in an exam question, you are far more likely to experience this type of queue because the examiner wants to see that you are aware that there will be empty spaces at the front. So even though a circular queue in reality is the much more likely thing that will exist in a computer, from an exam point of view, we want that theory side to demonstrate that understanding. I've already mentioned about a Stack Overflow. Well, with both of these 2 data structures, if we're trying to remove data that isn't there, we would create what's called an underflow. And if we're trying to add extra data in both the queue or the stack, that would be called an overflow. And we'd get an error in both situations. Okay, well, I just wanted to say thank you for watching. I really hope you found it useful and really hope you've learned something. Please do like and subscribe, and I'll hopefully see you again. Thanks a lot. Bye.